we've talked about sources producing potential differences between points in space. And we defined VB minus VA in terms of the integral of the electric field of the source as we go from A to B. But how do we calculate this? We've seen that for symmetric distributions, where we know the electric field, that's possible. But when our distributions are non-symmetric, the Gauss's law won't give us the electric field, and we need another approach. Now, we had an interesting thing for a point charge. If we had a point charge, and we started at infinity, and we ended at a distance r away, it doesn't matter how we got there, where this is a distance r from the source, then we had that the potential difference between r and infinity, so that's any point, here's where our A is, and here's where our B is, between these 2 points in space, was given by a very nice function, kq 1 over r. Now, it's this function that's going to be the starting point for a superposition principle. But first, what we'd like to do is choose a 0 point for our potential. And you can see there's a very natural place to choose a 0 point, so we're going to choose our potential at infinity to be 0. Sometimes in electrical engineering, the 0 point is referred to ground, but we'll call the potential at infinity to be 0. And that implies that we have a potential function for a point source, r. Let's always remember that v of infinity is 0. And again, when you see this function, it has a very physical meaning. It's if you take a test charge at infinity, you bring it to a distance r away from the source, you calculate using Coulomb's law, minus the work done, you divide by the test charge. It's precisely what this quantity is. But this begins to be a point, and you can see that if we looked at this function, where QS is positive, and we plotted V versus R, well, at the origin, there's a singularity, and it drops off like that. And when QS is negative, that same function goes to 0 at infinity, but it starts off as negative because the source here will be negative. And so these are our pictures of our potential function. And now what we want to do is we'd like to see what would happen if we have a continuous distribution of charges. How can we exploit this idea for a point charge to get an integral formula?